Take the mammals off this planet, every whale, every bat, every human, and ask how long before something else is running the place. Not long. The replacements are already here, and there are more of their species than of ours. The question is not whether reptiles come back. It is what has to happen to the Earth first. There is a steel drawer in a museum in Gainesville, Florida, and inside it, on gray foam, is a single bone from the middle of a snake. It is wider than your hand. It came out of the overburden of a working coal mine in northern Colombia, lifted off the top of a coal seam by a digger. This is not a film about a big snake. It is about what a body that size proves about the temperature of the world that grew it, and about who inherits a planet that goes back to that temperature. Because the last time it did, the reptiles got enormous, and the horses shrank to the size of a house cat. Pick it up. It is heavier than it looks, because fossil bone is not bone anymore, it is rock, about the width of a man's palm. Two smooth, articulating faces, one cupped and one rounded, that used to lock into the piece in front and the piece behind. A snake of this build carries a couple of hundred of them, laid end to end from skull to tail, and almost every one of them carries a pair of ribs. The animal is called Titanoboa cerrejonensis. It lived between 58 and 60 million years ago, in the wet tropics of what is now northern South America, roughly 8 million years after the asteroid, in a world that had just finished rebuilding itself. From nose to tail, the published estimate is 12.8 meters. The mass estimate is 1,135 kilograms. Longer than a city bus, about the weight of a small car. Both of those numbers come from Head and colleagues in 2009, and it is worth being exact about what kind of numbers they are. You do not weigh a fossil. You measure living snakes. Work out how the width of a vertebra scales with the length of the animal and run the fossil through that relationship. The bone is measured. The animal is calculated. Everything in this film will be labeled that way, because in a story that runs forward as well as backward, the difference matters. The rock came out of the Guajira Peninsula in the far north of Colombia, and it did not come out quietly. Cerrejón is an open-pit coal mine, the largest in Latin America, a hole in the ground you can see from orbit, worked by draglines and haul trucks the size of houses. The fossils sit in the overburden, the layer of rock that has to be stripped off and moved before the coal underneath can be taken. Paleontologists worked the spoil while the mine kept digging. And the snake was not alone in there. The same beds hold a turtle called Carbonemys, with a shell 1.72 meters across, a small dining table with legs and a head. They hold crocodile relatives, several species of them, in the same swamp as an animal that could eat them. They hold lungfish. They hold the leaf litter of a closed rainforest, the oldest one anybody has found. It is the first evidence anywhere of the kind of forest the Amazon is now, with the same layered canopy and the same families of plant. The insects had already started eating the leaves in the same patterns they use today. You can see the bite marks. This is the part that turns a curiosity into evidence. one enormous animal is an anecdote. An entire fauna running large, at every level, in the same water, is a condition. Because here is the thing about an animal that does not heat itself. Its body runs at the temperature its surroundings give it, and every chemical reaction inside it runs faster when that temperature is higher. Digestion. Growth, the speed of a muscle. A cold-blooded animal does not grow to the size it wants. It grows to the size its climate permits. Which makes this bone something stranger than a fossil. It makes it a measurement. And if the reptiles of that world were running at the top of what their climate allowed, there is an obvious next question, and the same rocks answer it. What were the mammals doing? Move forward 2 million years to 56 million years ago, and something goes wrong with the carbon. A very large quantity of it enters the atmosphere and the ocean. Where it comes from is still argued about. Volcanic intrusions into organic sediments, methane out of the seabed, some combination nobody has fully closed. What it does is not argued about. Global temperatures rise by 5 to 8 degrees Celsius, and they do it in 10 to 20,000 years. Geologists call it the Paleocene-Eocene thermal maximum. It is the closest thing in the rock record to a controlled experiment on a whole planet. The forests move north. The ocean turns corrosive at depth, and in the Bighorn Basin of Wyoming. In a stack of red and gray mudstone you can walk up in an afternoon, the animals are being measured against it, layer by layer. The one to watch is a horse. It is called Cyphrippus sandrae, and calling it a horse takes some imagination. It weighs about 5.5 kilograms, a small dog, a beagle. Something you could carry under one arm. It has 4 toes on each front foot and 3 behind, and teeth built for soft leaves rather than grass, because grass as a landscape does not exist yet. Then the heat arrives, and the horse gets smaller. Not by a little. Secord and colleagues in 2012 tracked it through the first 130,000 years of the event and found a drop of about 30% in body mass, from around 5.5 kilograms down to under 4. From a small dog to a house cat. Here is the detail that makes the study hard to argue with. The temperature record and the body size record come out of the same teeth. Oxygen isotopes in the enamel give you the climate. The size of the tooth gives you the animal. One specimen, 2 readings, no need to line up separate archives and hope they match. And then the planet cools at the far end of the event, and the horse grows back. Up to about 7 kilograms, larger than it started. That is the sentence to hold on to. It went down when the thermometer went up, and it came back when the thermometer came down. A one-way change is a coincidence. A change that reverses when the cause reverses is a mechanism. It also happens more than once. Later work found the same dwarfing at a second, smaller warming event 2 million years afterwards, in the same basin in unrelated lineages. Whatever this is, it is not about horses. Why it happens is less settled than that it happens, and it is worth saying so. Temperature is the leading explanation. Smaller bodies shed heat better, and there is a general tendency for warm climate populations of a species to run smaller than cold climate ones. But high carbon dioxide also degrades the nutritional quality of leaves. So a hotter world is also a poorer meal, and there are researchers who think that is doing at least some of the work. The two are hard to separate in a rock that recorded both at once. What is not in dispute is the direction. Nobody has found a hyperthermal in which the mammals got bigger. So put the two rocks side by side. In the Colombian tropics, at the warm end, a snake reaches 13 meters, and a turtle reaches the size of a table. In Wyoming, in the same greenhouse world, the earliest horse shrinks by nearly a third and then rebounds when it cools. Heat inflates the animal that does not heat itself. Heat deflates the animal that does. Most people watching this are not subscribed. If a snake that works as a thermometer is your kind of question, that is easily fixed. Now back to the drawer in Gainesville and the rest of that world. Strathcona Fjord on Ellesmere Island in the Canadian High Arctic. The ground is frost-shattered rock in every direction. There is no soil worth the name and no tree of any kind, because nothing woody survives here. The wind comes off the ice, and the summer lasts about 6 weeks. This is 78 degrees north, about 1,300 kilometers from the North Pole. Now take the same ground 52 million years ago. It is swamp. Standing brown water under a canopy of dawn, redwood, and swamp cypress, the trees rooted straight out of it, the light coming down green. There is leaf litter a meter deep. There are insects in the air in numbers that make the air look dirty. And in the water, there are alligators. Not a metaphor, and not a warm month visitor, the Eureka Sound beds on Ellesmere have produced alligator relatives. They have produced champsosaurs, long-snouted aquatic reptiles that looked like gharials and were not. They have produced snakes, lizards, and giant land tortoises the size of a coffee table. Estes and Hutchison described the first of them in 1980. Expeditions have been adding to the list ever since. The obvious objection is that the continent must have moved. It has not moved enough. Ellesmere was at high Arctic latitude then too. The plate has drifted a few degrees, not 40. These animals were living inside the Arctic Circle. So how cold did it get? Eberle, Frick, and colleagues in 2010 went at it with oxygen isotopes from the bones and teeth of the animals that live there together. Fish, turtles, mammals. They put the coldest month at somewhere around 0 to 3.5 degrees Celsius, with the warmest month near 20. Read that again, slowly. An Arctic winter no colder than a mild January in London. But there is one thing that no amount of carbon dioxide can touch, and it is the thing that makes this chapter strange rather than merely warm. At 78 degrees north, the sun drops below the horizon in late October and does not come back until February, close to 4 months of darkness. That is not climate, that is geometry, the tilt of the planet against its orbit, and it was exactly the same 52 million years ago as it is tonight. So these animals did not simply enjoy a warm Arctic. They fed, bred, grew and overwintered through a third of every year in the dark, on an energy budget that had to survive months with almost nothing coming in. A tortoise can do that. A crocodilian can do that. It is not clear that anything with a mammal's fuel bill could have done it at that body size, and the large mammals of that fauna are conspicuously absent. The forest had the same problem and solved it the same way. Dawn redwood is deciduous. It drops the whole canopy in autumn and stands there as bare wood for a third of the year, which is an odd thing for a conifer to do and exactly the right thing to do if the sun is going to switch off. The fossil beds are full of the dropped needles in mats season after season. That is the picture to hold. Not a tropical Arctic, a cool, wet, dim forest that shut down every winter, with alligators in the water and tortoises on the bank, all of them doing the one thing a low-cost body is best at. Waiting, which brings the drawer in Gainesville back into the frame. Same lineage, same greenhouse world, opposite end of the planet, 13 meters of snake at the equator, alligators inside the Arctic Circle. Not a refuge, a range, and that closes the first half of the case. A hot world does not only change how big these animals get, it changes where they are allowed to be. It opens ground that was shut. Which leaves the question this whole film turns on, and it is a question about mechanism. Why should heat be an advantage to them at all? Here is the question stated plainly, because everything from here is an attempt to answer it. The last time this planet ran hot, reptiles got enormous and mammals shrank. The planet is heading back toward hot. So is the next age of Earth theirs again, and what exactly would have to happen to us for that to be true? Start with the fuel bill. If you take a lizard and a mouse of exactly the same weight and follow both of them around in the wild with isotope tracers, measuring what they actually burn over days rather than what they burn on a lab bench, you get a gap that is hard to believe the first time you see it. The reptile runs on somewhere between 1/12 and 1/20 of the mammal's energy. Put it in food. The lizard eats in a month what the mouse of the same weight eats in about 3 days. That is not a difference in efficiency. It is a difference in what the animal is doing with the food. You are doing it right now. Sitting still, reading nothing, moving nothing. Your body is holding itself at 37 degrees Celsius against whatever the room is doing. And most of the calories you ate today went into that and nothing else. Not movement, not thought. Heat. A mammal is a house with the heating left on. Every hour, every season, awake and asleep, in summer, in the dark, whether or not there is anything to eat that week. The bill does not pause. And now the honest other side of it, because a film that only argues one way is not worth watching. That bill buys an enormous amount. It buys speed on demand, at 4 in the morning, at temperatures where a lizard is a stone. It buys sustained endurance, which is how a wolf runs down something faster than it is. It buys cold ground, every mountain, every winter, every pole. It buys the constant internal chemistry a large brain needs to be worth its cost. In a rich world, the expensive animal wins. That is not a theory. It is the last 66 million years. Mammals got the megafauna jobs, the polar jobs, the night jobs, and the ocean. So the mechanism is not that heat is good for reptiles. The mechanism is that scarcity is survivable for them. Which is exactly what the record shows at the worst moment in the last 100 million years. 66 million years ago, the asteroid hits, the sky closes, photosynthesis stops for some months to some years, and the food supply of the entire planet is switched off. Every non-avian dinosaur dies, every single one. The crocodilians do not. They lose lineages. This is not a story about them shrugging it off. But the crown group comes through, in freshwater, on a body plan that can wait. An adult crocodile can go months without a meal and lose almost nothing. It is not that they were tougher. It is that they were cheaper. That is the whole argument in one animal. When the world is generous, being warm is an advantage worth paying for. When the world stops being generous, the same body becomes a standing debt. So the question narrows. How hot does it have to get before that debt is called in? And to answer it, you need a thermometer that works on deep time. Which brings us back to the drawer and to a fight, in the pages of one journal, about whether that bone can measure anything at all. The drawer in Gainesville again. The vertebra, the gray foam, the width of a palm. In 2009, Head and colleagues published that bone in Nature and did something more ambitious than describing a large snake. They used it as an instrument. The reasoning runs like this. A snake's body temperature is the temperature of its surroundings. A bigger animal has proportionally less surface to shed heat through and a slower metabolism per kilogram. So there is a maximum size a snake can reach in any given climate, and, run backwards, a minimum climate any given snake requires. Feed 13 meters into that, and the answer that comes out is a mean annual temperature of 30 to 34 degrees Celsius. Be careful with what that means, because it is easy to hear it as a hot afternoon. It is an annual average, every night included, every wet season included. The whole year averaged flat at 30 to 34. Today, the equivalent figure for the wettest tropical lowlands is around 26 to 28. The response arrived in the same journal later that year. Denny, Lockwood, and Samaro looked at the same animal and said it could not have been that warm, for a reason that sounds like a contradiction and is not. A snake that heavy has an enormous thermal mass and very little surface area to lose heat through. Its own metabolism generates heat that it cannot easily dump. Put that animal in an environment averaging 34 degrees, and by their calculation, it does not thrive. It cooks slowly from the inside. Their figure was lower, around 27 to 29 degrees. Their title was blunt: Can the giant snake predict paleoclimate? Head and colleagues replied on the facing pages, arguing that the critique had misread the model, that they had never assumed a body temperature locked at a fixed offset from air temperature, which is the assumption the objection was built on. Nobody conceded. It has been more than 15 years and nobody has conceded. Both papers are still standing, both numbers are still cited, and if you want a picture of how paleoclimate actually gets done, this is it. 2 teams, 1 bone, and a disagreement of 5 or 6 degrees that neither can close. This is not a weakness in the science. It is the science. The uncertainty is stated, published, argued in the open, and it is exactly the kind of gap that gets closed, finding another line of evidence rather than by shouting. So look for another line. There is one in the same rock, and it does not come from animals at all. The shape of a leaf tracks climate. In wet, warm forests, leaves tend to be large with smooth, unbroken edges. In cooler places, they get smaller and their margins get toothed. Wing and colleagues in 2009 ran that analysis on the plant fossils from these beds, 3/4 of them large and smooth-edged, and got rainfall above 2,500 millimeters a year and a mean annual temperature above 25 degrees. Which is a floor, not a referee. It sits underneath both estimates and rules out neither. 3 independent methods, and the argument survives all 3. And notice what the argument is not about. Neither team suggests the Paleocene tropics were like today's tropics. The dispute runs between 27 and 34 degrees. Today's wettest lowlands brush the bottom of that range and come nowhere near the top. The low estimate is the floor, not the answer, and the animal in the drawer does not exist in a world at today's temperature under anybody's model. So the reptile end of the scale is contested at the top, but firm at the bottom. They were living at temperatures we do not currently have, which raises the obvious symmetric question, and it turns out to have a much sharper answer. If that is roughly where their ceiling sits, where is ours? Stand in still air at 40 degrees with the humidity high and no wind. Nothing is happening to you that you can see. Underneath, your body is running an emergency. Blood goes to the skin, sweat glands open. Roughly half a liter an hour leaves you as water, and the only reason you survive the next hour is that the water evaporates and takes heat with it as it goes. That is the entire system. Mammals have exactly one trick for shedding heat, and it is evaporation. Your core sits at 37 degrees. At 40, you are in trouble. Between 42 and 43, proteins in your cells begin to come apart, and the damage does not wait for a doctor. That is 5 degrees. 5 degrees of headroom for the entire mammal lineage, from a shrew to a blue whale. Everything a mammal has ever done, it has done inside that band. Now the number that matters, and it is not the one on the weather forecast. Wet bulb temperature is what you get if you wrap a thermometer in a wet cloth and blow air across it. It is the coldest that evaporation alone can make something in that air. In dry air, it sits far below the air temperature, which is why 45 degrees in Arizona is survivable. In saturated air, it climbs to meet the air temperature, and evaporation stops being able to do anything. When wet bulb reaches your skin temperature, sweat no longer cools you. Shade does not help. Rest does not help. Drinking does not help. You are producing metabolic heat with no exit. Sherwood and Huber in 2010 put that threshold at a wet bulb of 35 degrees, and that figure went into a decade of papers as the limit of human survivability. Then Veselio and colleagues in 2022 did the obvious thing and tested it on people. Young, healthy, fit volunteers in an environmental chamber at rest, monitored continuously. The point at which core temperature began climbing, with no recovery, came earlier than the model said, nearer 30 to 31 degrees wet bulb, depending on the conditions. 2 teams, 2 numbers. And this disagreement runs in one direction only. The measured limit is lower than the modeled one. Nobody has argued it is higher. There is one more number, and it is the one that moves this out of the future tense. Raymond, Matthews, and Horton went through 4 decades of weather station records in 2020 and asked a simple question: has a wet bulb of 35 ever actually been recorded? The answer was yes. At least a dozen times since 1979, for an hour or two at a stretch, at coastal stations around the Persian Gulf and in the Indus Valley, one of them the airport at Abu Dhabi. Extreme humid heat overall has more than doubled in frequency across the same period. The models had put the first occurrence somewhere near the middle of this century. It had already happened, in bursts, and nobody noticed because nobody was looking at that variable. Now set that against the animal in the drawer. The desert iguana of the American Southwest holds a preferred body temperature of 40 to 42 degrees Celsius. It works there. It hunts, digests, and mates there. Its critical maximum, the point at which it loses coordination, is somewhere near 47. Read those 2 paragraphs together, and you have the whole asymmetry of this film. The lizard's comfortable afternoon is the temperature at which a human being dies. And that is the mechanism, finally, stated in full. Reptiles do not need heat in order to win. They do not outcompete us. They do not evolve some new advantage. They simply do not have the wall that we have, and they never did. Every advantage endothermy bought was bought against a fixed internal temperature. The speed, the range, the cold ground, the brain, and that temperature has a fixed distance to failure. Which means the reptile case does not rest on reptiles at all. It rests on us hitting something they do not hit. Except that they do hit something. And it is already happening, on beaches and hillsides, right now. Everything so far has been the case for the reptiles. Here is the case against it, and it is stronger than most people telling this story will admit. Start with the thing that sounds like it should be impossible. Warming is killing lizards. Not by cooking them, by locking them indoors. A lizard's day is a schedule. It comes out, warms on a rock, reaches working temperature, and then has a window in which to hunt, feed, defend a territory, and find a mate before the ground gets too hot and it has to go back under cover. Raise the ambient temperature by a few degrees, and that window does not shift. It closes from both ends. Cernervo and colleagues in 2010 measured this across 5 continents. They went back to sites where lizard populations had been surveyed decades earlier and counted what was still there. 4% of local populations worldwide. Already gone since 1975, not displaced. Gone. Their projection for 2080 was 39% of local populations extinct and around 20% of lizard species lost outright. That is a model published with its assumptions, and models get revised. The 4% is not a model. That part is a count. The animals were not dying of heat. They were starving inside a shortened working day. And then there is the egg. In every crocodilian and in most turtles, the sex of the hatchling is not written in its chromosomes. It is set by the temperature of the nest during a critical window of incubation. A difference of a couple of degrees in the sand decides whether an egg becomes male or female. That system worked for something like 100 million years. It is failing now in the open, where anyone can go and count. Jensen and colleagues in 2018 sampled green turtles feeding on the Great Barrier Reef and worked out which beaches each animal had hatched on. From the cooler southern beaches, the sex ratio was skewed but functional, around 2 females to every male. From the warmer northern beaches, among juveniles, the figure was 99.1% female. Among the slightly older animals, 99.8%. Effectively, no males have come off those beaches in years. The population does not collapse immediately, and that is the trap in it. A green turtle takes decades to mature, and a male can service several females. So the adults in the water today were hatched in a cooler century, and the numbers still look survivable. The failure is loaded into the future by 30 or 40 years, which is the worst possible design for a problem anyone has to notice in time. This is the structural weakness, and it is worth naming precisely. A mammal incubates internally. It carries its thermostat with it into shade, into water, underground. A reptile digs a hole, lays, leaves, and hands the most important decision in the animal's life to whatever the ground happens to do for the next 2 months. So the obvious conclusion is that reptiles are not the inheritors at all. They are the first casualties. Except that the record keeps refusing to be that simple. Holily and colleagues in 2015 worked on central bearded dragons in Australia, a lizard with proper sex chromosomes, where genetics decides. At high incubation temperatures, animals with male chromosomes develop as fictional females instead. They breed, they lay, and their daughters inherit a lineage in which the chromosomal system has been abandoned entirely, replaced by temperature. That was found in the wild, not just the lab. The system did not fail. It converted. How general that is, nobody knows yet, and anyone who tells you otherwise is ahead of the evidence. It has been demonstrated in one species and looked for in others. So, put the balance honestly. Nothing here is a coronation. Everything alive is being pushed, reptiles included, and some of them are being pushed off the edge right now. The question was never who is comfortable. The question is who has the shallower cliff. And to see the cliff properly, you have to go a very long way forward. $250 million years from now. What follows is not a forecast. It is one published reconstruction run on things we can measure, and I will show you where the teams disagree. You are standing in the middle of a continent. Not near the middle, the middle. The nearest coastline is thousands of kilometers away in every direction, and the air that reaches you crossed all of it as dry land. The ground is bare, not sand. Sand takes rock and weather, and here there is barely enough water to make either. It is hardpan, cracked into plates, pale enough to hurt to look at. Nothing is moving, and the reason nothing is moving is not that the land is empty. It is that it is the middle of the day. This is Pangaea Ultima, the next supercontinent in the reconstruction published by Farnsworth, Scotese, and colleagues in 2023. There are rival maps. Mitchell and colleagues argue in 2012 for a different assembly, closing the Arctic instead of the Atlantic, and calling the result Amasa. Which map wins is a story for another film. What they share is the shape of the problem: one mass of land and an interior no ocean can reach. Three things arrive at once in that model, and they stack. The first is the continent itself. Put all the land in one piece and the middle of it stops having a climate in any useful sense. No maritime moderation. Enormous swings. Sustained land temperatures above 40 degrees Celsius across most of it. The second is carbon dioxide. Their runs put it between 410 and 1,120 parts per million, driven by volcanism along the new seams and by the loss of weathering surfaces. Today, measured on Mauna Loa, the figure is just above 420. So the low end of that future is roughly now, and the high end is nearly 3 times it. The third is the sun, and the sun is the part with no argument attached. Goff calculated it in 1981, and the number has held. Solar output rises by about 1% every 110 million years, as hydrogen in the core gives way to helium and the core contracts and heats. By that date, the sun is around 2.5% brighter than it is tonight. It does not turn back down. There is no scenario in which it turns back down. The result the paper is known for is a single figure. Farnsworth, Scotese, and colleagues estimate that between 8 and 25% of that supercontinent's land stays inside mammalian tolerance. The range, depending on how much carbon dioxide the models are given, with 8% at the high carbon end. Today, the equivalent number is about 66%. 3 out of every 4 dryland acres closed. And the fraction that stays open is not scattered conveniently about. It is coastal margins and the higher latitudes. Narrow strips at the edges of a continent whose interior has become the largest continuous desert the planet has ever assembled. Everything that needs a fixed body temperature is pushed to the rim. And here is where honesty costs the thesis something. That model does not hand the planet to lizards. Above roughly 40 degrees, sustained, an ectotherm is not comfortable either. It is at the top of its own range with nowhere left to go, and the foraging window problem from the last chapter becomes permanent. Further out still, Caldera and Casting argued in 1992 that the brightening sun eventually drives the carbon dioxide plants need below the level photosynthesis can work with, somewhere on a horizon of 600 million to a billion years. When the plants go, the argument about who eats them is over. Somewhere in that world, a large animal dies in the mud of a shrinking waterhole, and one bone from the middle of it is buried and mineralized and waits, wider than a palm, with no particular reason to expect that anyone will ever open a drawer and pick it up. There is a word in the title of this film that is wrong, and it has been wrong from the first minute. Again, because reptiles are not coming back. They never left. Birds are archosaurs. They sit inside the same branch of the family tree as the crocodilians and the dinosaurs, and they are not merely related to dinosaurs. They are dinosaurs, the one lineage that came through the asteroid on feathers. If the word reptile means anything as a branch rather than as a look, every bird alive is one. There are about 11,000 species of them, and there is one within 100 meters of you right now. So do the arithmetic properly. Non-avian reptiles alive today. Roughly 12,400 species of lizard and snake, about 360 turtles, 27 crocodilians. Mammals, about 6,600. Add the birds, and it stops being close. Reptiles outnumber mammals on this planet by something like 3.5 to 1, and they have done for the whole of what we call the age of mammals. We did not take the planet. We took the large-bodied jobs, and we kept the microphone. And that mammal column is thinner than it looks. Baron, Phillips, and Milo weighed it in 2018. The total mass of every mammal on Earth, sorted. 96% of it is human beings and the animals we raise to eat. Every wild mammal left, from the blue whale down to the last shrew, is the remaining 4%. That is not a projection. It is an inventory, taken now. Which means the age of mammals, described honestly, is a handful of wild lineages and one enormously successful primate with its livestock. It looks like dominance from inside it. From the rock, it will look like a spike. So, is the next age of Earth a reptile age? Yes, in a sense, nobody means when they say it. And no, if what you are picturing is lizards moving into our exact jobs, because most of those jobs will not exist. What comes back is not a species, it is a rule. For 66 million years, holding your body at a fixed temperature has been the winning move on this planet, and the world has been generous enough to pay for it. The evidence in the rock, in the drawer, in the isotopes, and in the models says that arrangement is a condition, not a law, and conditions end. In Gainesville, a hand puts the vertebra back on its gray foam. The drawer slides shut. Somewhere in the dark of that cabinet, a bone from the last hot world sits waiting for someone to work out whether it is a fossil or a forecast. Next time on this channel, the ocean that is already closing 1 centimeter a year, and the single landmass its death is building. If you want the rest of this story as it goes out, subscribe. There is a new one every week. Built the same way, the evidence first, and then wherever it goes.